Hey everybody, it's Thursday, March 4th, and as you can see here in the aim today, our goal for today's video is all about how we can apply our understanding of accelerated linear motion to rotating bodies. Now, like I wrote here, the vast majority of today's video is going to be about accelerated motion. But before we get into that, I think it is appropriate for us to spend a couple minutes talking about the key takeaways from yesterday's video. And so basically, we're just going to make a list here. The first thing I want to put on this list, which is probably the most important note we can write about rotational motion, is that every quantity in rotational motion has a linear analog, a version in rotational motion, if you will. And so, as we saw yesterday, we have in linear motion concepts like position and displacement. And essentially what we were saying yesterday is just that there's a rotational version of that. Those are called angular position and angular displacement, which brings us to our next bullet point. As position and displacement are measured in linear motion in meters on Cartesian coordinate axes, angular position and angular displacement are measured on a polar coordinate axis in terms of the radius, the distance from the center, and the angle. So here's the deal. If we are trying to locate a point on a Cartesian coordinate axis, like just a regular old XY axis, we say the point is here. And so its Y coordinate is this, and its X coordinate is this, and that's its location. On a polar coordinate axis, we measure the angle and how far the object is away from its center. So if we were trying to locate that same point, we would say it's this distance r from the center, and the angle is measured from that reference axis. And so we would say, it's 2 meters out at some number of degrees. Whereas in an XY coordinate axis, we have, the X coordinate and the Y coordinate. And so that's how we make these measurements. Speaking of angles for measurements, all angles in this course for rotational motion are measured in radians. When we are talking about the angular position or the angular displacement or even the angular velocity, we are always going to be using the angle measure radians instead of degrees. That's another very important point as well. As we also went on to say at the end of yesterday's video, angular velocity is a measurement of the rate of change of angular position. That's another important point here. And lastly, and this was probably one of the more confusing things, and it really wasn't explained much yesterday, so I want to flesh it out a bit more today. Angular velocity is positive when the object is rotating counterclockwise, and negative when the object is rotating clockwise. Now, this might seem like it could be backwards, but it actually makes a lot of sense if you think about it. Mostly because everything in our world is based on right-handedness. And so my fellow lefties will, feel the struggle on this one. But the way we determine the direction of the angular velocity ultimately has to do with a right-hand rule. And it works pretty simply. Basically, what we do is we take our fingers on our right hand and we curl them in the direction of the rotation. And that means then that our thumb points in the direction of the angular velocity. So if you think about looking at this disk here on the left, you'll notice here it's rotating this way. And if you were looking at it from above, it would be rotating counterclockwise. And so if we curl our fingers in the direction of the rotation, our thumb points up. The thumb direction here is actually the direction of the angular velocity. Of course, it works the same way for the other direction of rotation. If the thing is rotating like this, if we were looking at it from above, it would be rotating clockwise. And so we curl our fingers in the direction of rotation, the thumb points in the direction of the angular velocity, which in this case is down. And it does seem to make sense here that if the angular velocity vector is up, it would make sense to call the direction of rotation then positive. And if the thumb is pointing down, it would make sense to call that direction of rotation negative. And so that's where it comes from. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so just to drive home a key point here, key idea, While the direction of rotation can be described as being clockwise or counterclockwise, it's important to realize the direction of the angular velocity is always perpendicular to the plane of rotation. So if you have an object rotating, like if you're looking at a clock, for example, the direction of the angular velocity would be into the face of the clock or out of the face of the clock if you've got the hands to run backwards. That's the idea. Take a second to pause this video here and write that down. And when you hit play, we'll move on to angular acceleration. So that brings us to angular acceleration. And what we can say about angular acceleration here is pretty straightforward. Remember, this is simply the rotational version of linear acceleration. What we define linear acceleration as is pretty straightforward. Linear acceleration is the rate of change of velocity. And so it should be no surprise to anybody that angular acceleration is the rate at which the angular velocity changes. And as a result, the equation is going to take a form that's going to look totally familiar to you. Before we take a look at the equation, of course, we have to look at the symbol, because now this is yet another new variable. We need another new symbol. And as I mentioned yesterday, almost all of these rotational motion variables are Greek letters. The angular acceleration symbol is actually a Greek letter that should look familiar to you. It is a lowercase alpha. And so I'll actually go ahead and write that next to this. This is a lowercase alpha. And so notice in this font, it looks a little like short and compressed. The tails aren't that long. Usually when I write it out, I make it look something more like that. Either way, it's the same symbol. It's an alpha. And so the equation, rather unsurprisingly, looks like this. In exactly the same way as the acceleration is the change in velocity over time, and so that would be v final minus v initial over t, the angular acceleration is the change in angular velocity over time. And so that would be the final angular velocity minus the initial angular velocity over time. And that's it. Just to define our symbols here, delta omega is the change in angular velocity, of course, measured in radians per second. Omega final is the final angular velocity, omega with the subscript f. Omega naught is the initial angular velocity. T, of course, is the time. And the angular acceleration is going to be measured in units of radians per second squared. This works exactly the way it worked for linear acceleration. For linear acceleration, we always had meters per second divided by seconds is meters per second squared. And so here we have the change in angular velocity measured in radians per second divided by seconds is going to go ahead and give you radians per second squared. And the way that we should interpret it should be exactly the same as the way we interpret meters per second squared. When we look at a measurement, and let's just say it's 5 meters per second squared, we say, well, that means the velocity is changing by 5 meters per second. Here, it's the exact same thing. When we see an angular acceleration of 5 radians per second squared, we say the angular velocity is changing by 5 radians per second. And of course, then the unit, as we already mentioned, is radians per second squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So let's take a look at a problem. Let's just see how this works in the context of the problem. It says here, the interior of a plane's engine moves uniformly from rest to an angular speed of 75 revolutions per second in 55 seconds. And the question says, determine the angular acceleration in radians per second squared. Now, I think it's important to make a mental note of something that I'm about to say right now. This unit is going to be annoying for homework assignments from the packet. And that's because all of the textbooks that we are looking at, the textbooks which comprise your packets, are American textbooks. And the standard rotational unit in America, usually, at least for American engineers, as you know from shop, is either revolutions per second or revolutions per minute. But in physics, the natural unit is radians per second. So the basic idea here is for a lot of these textbook problems, we're going to have to do conversions. I do not want you to write this down every time you solve a problem. And by write this down, I mean, I don't want you to show the work. I just want you to write the numbers. You go ahead, you do it in your calculator, and then you write down the result. So for this problem, I will show it. I will probably show it for all the problems for today, but for the future, all you really need to do is just write down the answer. So what do I mean here? Well, they're telling us here we have 75 revolutions per second for our angular speed. And what I need is a measurement in radians per second. And so I have to do a little dimensional analysis. Now, this is the part ultimately you're going to be doing in your calculator. So we need to make the revolutions cancel, so I'm going to put that on the bottom. And the question is, how many radians are in one revolution? How many radians are in one full turn? And the answer is 2 pi. And so when you want to convert something from revolutions per second to radians per second, all you need to do is go into your calculator, take 75 times 2 pi, and just write down the number in your list of knowns. You don't actually have to show this work here every time. And so what you'll notice when you do this in your calculator is your calculator will tell you 75 revolutions per second is 471.24 radians per second. Another little note to make about this is you also always want to preserve the number of sig figs in the original measurement. Pi is an irrational number. And so the number that you're going to get when you're doing these conversions is always going to have a ton of decimal points. You don't want to write all those down. 75, as it's written in the problem, has 2 sig figs. And so we're going to call this 470 radians per second. And now we're in business. The interior of a plane's engine moves uniformly from rest to an angular speed of 470 radians per second in 55 seconds. And we're looking for the angular acceleration in radians per second squared. So our initial angular velocity here is going to be 0 radians per second. They tell us the thing is initially at rest. Our final angular velocity, as we just saw, was told to us to be 75 revolutions per second, but we calculated that as 470 radians per second. The time, as given in the problem, is 55 seconds, and we're looking for our angular acceleration, which is alpha. According to the equation that we showed here at the beginning, alpha, the angular acceleration, is equal to the final angular velocity minus the initial angular velocity over the time. And so here, this is going to work exactly like a standard acceleration problem. We have 470 radians per second minus 0 radians per second over 55 seconds. And when you do that math, 470 over 55, you get 8.5 radians per second squared. And again, we're just going to call it 8.5 because the number on the calculator comes out to 8.54545454. And so we're going to call it 8.5 to 2 sig figs. And that's in radians per second squared. And so what that means is omega changes by 8.5 radians per second. And that makes sense because if it changed by that amount, 8.5 radians per second each second for 55 seconds, it would eventually get up to 470. That's it. That's really all there is to it. Pretty straightforward. Take a second to pause this video here and make sure you have this whole solution written down. And when you hit play, we'll move on. Okay, so let's just take a second to write down a quick note about the conversions. For these conversions, note, to convert from revolutions per second to radians per second, you simply multiply the measurement by 2 pi. And so if you have x number of revs per second, you multiply by 2 pi 2 pi radians over 1 revolution, and that gives you your measurement in radians per second. On the other hand, if you're converting from revolutions per minute to radians per second, you multiply the measurement by 2 pi over 60. And again, you don't need to go nuts about showing work here. Let's just say you have x number of revolutions per minute. Of course, to cancel out the revolutions, we've already shown that you need 2 pi radians over 1 revolution. But if you want to cancel out the minutes, then you have to put 1 minute over 60 seconds. So the end result here is basically multiplying by 2 pi over 60. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Before we move on to the next topic here, let's just make sure that everybody is with me on this one. Let's take a second to ask a question. Question: would doubling the angular acceleration during the given time period have doubled the final speed? Would doubling the angular acceleration during the given time period for that last problem double the final speed? Take a minute to pause this video here and think about what the answer is and why the answer is what it is. And when you hit play, we'll go over it. Okay, and the answer here, pretty straightforward. Since the angular acceleration is directly proportional to the change in angular velocity, if the angular acceleration was doubled, then yes, the angular velocity would be doubled. Now, the other reason to bring this up, I think, is because you could say the angular acceleration is directly proportional to the change in angular velocity, and you realize that that looks a little weird. So this proportional symbol that we've been using here, the alpha, don't want to use it for angular acceleration because it just looks weird. And so just use the words directly proportional for that one. It may be confusing to somebody who's grading your AP test. Obviously, I know what you were talking about, but I think it's important just to keep that straight. Remember, all the relationships for regular acceleration or linear acceleration apply to angular acceleration in exactly the way you would expect. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so that brings us to what we are going to discuss for the rest of this video here, which are the kinematic equations. When we were discussing linear acceleration after we finished talking about the actual acceleration equation, we got into kinematic equations. We are going to do the same thing here. In accelerated linear motion, we saw there were 4 major equations for accelerated motion. Using the idea that every rotational variable has a linear analog, we can simply replace the linear variable with the rotational variable to come up with our kinematic equations for rotational motion. And that's what we're going to go ahead and do now. Use those to solve some problems, and then that'll be it for today. Take a second to pause this video here and write that down. When you hit play, we'll move on. And so we'll start with the final velocity equation. Remember, what we are referring to as the final velocity equation is the equation V final equals V naught plus AT. And so as we said, all we need to do is replace the linear variable with the rotational variable. The V's are going to become omegas, and the A's are going to become alphas. And so this equation is just going to look like this. Omega final equals omega initial plus alpha t. It really is that simple and straightforward. And so in this equation, omega final equals the final angular velocity measured in radians per second. Omega naught equals the initial angular velocity measured in radians per second. Alpha is the angular acceleration measured in radians per second squared. And of course, t is the time measured in seconds. Take a second to pause this video here and write that down. When you hit play, we'll move on. Okay, moving on here. Now we have the displacement equation. Remember, the displacement equation in the reference table is written like this. X equals x naught plus v naught t plus 1/2 at squared. And when we needed to use it, especially if they were just asking us for the displacement, oftentimes we would just write delta x equals v naught t plus 1/2 at squared. And so pretty simply, x is the displacement, so we're going to replace that with angular displacement, or delta theta. V naught, of course, initial velocity, we're going to replace with initial angular velocity. Acceleration, we're going to replace with alpha, angular acceleration. And time is time. And so the equation is going to look like this if we are writing it in terms of the angular position. And I guess I'll write here in parentheses, angular position. Or we'll write it in terms of the angular displacement like this. Delta theta equals omega naught t plus 1/2 alpha t squared. This, of course, like it was the case for linear motion, has 2 versions, whether we're solving for displacement or position. But the equation looks like this. And so theta, without the subscript f in the reference table, of course, if you put the subscript f, it's fine by me. Theta is the final angular position. Theta naught is the initial angular position. Both of those are measured in radians. So is the angular displacement, which is given the symbol delta theta. Omega naught is the initial angular velocity. Alpha is the angular acceleration measured in radians per second squared. And t is the time. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on now to the last equation, we have our time-independent equation. And in a way that's not going to surprise anybody, the time-independent equation, as we wrote it when we were talking about kinematics, was vf squared equals v naught squared plus 2a delta x. And so we have our final velocity squared equals our initial velocity squared plus twice the acceleration times the displacement. And so we are going to have omega replacing the v's, alpha replacing the a's, and of course delta theta replacing our delta x. And so the equation should look like this. And so here, of course, our omega final is our final angular velocity measured in radians per second. Omega naught is the initial angular velocity measured in radians per second. Alpha is the angular acceleration measured in radians per second squared, and delta theta is the angular displacement measured in radians. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the reference table. And so if you look at the reference table, you will notice at the very top are your three equations that we just went through. And as you scroll down, you will see those equations for their rotational version. Something that's kind of weird, if you just go down and look, something that's kind of weird in this course is that they don't put the time-independent rotational motion equation for some reason. It is an equation. It is available to you. Of course, you shouldn't go nuts about any of these equations because they really are just a rotational version of these equations. But at the end of the day, 2 out of the 3 are in the reference table. As is the case for the acceleration equation is not in here, but you can always solve for it from the final velocity equation, which is there. And that is it. Let's go ahead and solve some problems. This problem here is in the rotational motion packet. It's on page 3, number 18. It says a centrifuge accelerates uniformly from rest to 1,500 revolutions per minute in 240 seconds. And the question says, through how many revolutions did it turn in this time? So there are a number of ways that you can solve this problem, but the first thing that we have to do is we have to do our conversion for omega final. Since I've never shown one of these, I'm going to show it here. Again, in the future, you can just write it in your list of knowns, but here we have 15,000 revolutions per minute. And so we got to multiply by 2 pi radians over 1 revolution to cancel the revs and get radians, and then 1 minute over 60 seconds to cancel the minutes to give us seconds in the denominator. And when you multiply 15,000 by 2 pi divided by 60, you get 1,570.8 radians. Now, of course, radians per second. Of course, though, 15,000 only has 2 sig figs. And so we're going to have to call that 1,600 radians per second. Now we're ready to solve the problem. Now, notice, I understand, I want to just preface this here. I understand the question says through how many revolutions, so we are actually going to find the answer in radians and then go ahead and convert it back. Most of that is just so you can see how these conversions are done. Once you have that down, then it's not really going to be an issue, but that's at least the idea. So it says here, we've got this thing accelerating from rest, so that means our omega naught is going to be 0 radians per second. As we mentioned here, our omega final is 1,600 radians per second. The time is going to be listed as 240 seconds. And we're looking for delta theta. Now, of course, this is a nice 2-part problem here because we cannot find delta theta with any of the equations we have unless we know the acceleration. So first, we'll have to find the angular acceleration here, which is alpha, and that's equal to omega final minus omega initial over the time. And so our angular acceleration here is going to be 1,600 radians per second minus 0 radians per second over 240 seconds. And that's going to give us an angular acceleration here of 6.7 radians per second squared. Now, you have a choice as to what equation you want to use for the second part, because both equations with delta theta in them will work. But I'm just going to go ahead for no reason and just choose omega naught t plus 1/2 alpha t squared is equal to delta theta. Now, this equation is nice to use because the omega naught t goes to 0 because this thing starts from rest. And so we just have delta theta equals 1/2 alpha t squared, which should look very familiar to you. We use this a lot in linear motion, just the linear version. And so we have 1/2 the acceleration, or the angular acceleration, which is 6.7 radians per second squared. And then we're going to multiply that by the time squared, which is 240 seconds, whole thing squared. And when we do that math, we end up with delta theta is equal to 192,960 radians. But of course, because we want to round this thing to 2 sig figs, we're going to call it an even 190,000 radians. Now, of course, the question said through how many revolutions? So we're going to have to do that conversion. So we have 190,000 radians, and to convert that to revolutions, we're going to say here 1 revolution is 2 pi radians. We're putting the radians in the denominator so they cancel, and basically we're going to take our 190,000 and divide it by 2 pi. When you do that, you get 30,239.4, a bunch of other numbers in there for your revolutions. And so to 2 significant figures, we will call that 3.0 times 10 to the 4 revolutions, or about 30,000 revolutions. And that is our final answer. Take a second to pause this video here and make sure you have all that solution written down. And when you hit play, we'll move on. Moving on to another example here, let's just take a look at one more, and then I'll have you try one on your own. This problem here says pilots can be tested for the stresses of flying high-speed jets in a whirling human centrifuge, which takes 1 minute to turn through 23 complete revolutions before reaching its final speed. What was its angular acceleration, assumed constant, and what was its final angular speed in RPM? So we're going to go ahead and do this again in this sort of more complicated style. For delta theta, first we're going to convert 23 revolutions to radians. And so we have 2 pi radians over 1 revolution. And when you take 23 and you multiply it by 2 pi, you get 144.513 radians. But we're going to call that 140 radians. And so now, going through our list of nodes here, it does not say, but you have to realize this goes back to all that stuff about the assumptions we make. It should be assumed that the thing starts from rest, because the person can't get in it if it's moving, right? So we'll say here our omega naught is 0 radians per second. The time, it says, is 1.0 minute, so we'll call that 60 seconds. So everything is to 2 sig figs here. Our delta theta, they told us, was 23 revs, but we just calculated here that was 140 radians. And that's it. We're looking for the omega final. And so, as was the case for the last problem, we cannot find anything we need to find, specifically the omega final, without the acceleration. Now, of course, what's a little complicated about the acceleration is that we can't find that using the traditional equation because we don't have the final angular velocity. And so what we're going to have to do here is use the equation delta theta equals omega naught t plus 1/2 alpha t squared. This thing starts from rest, so the omega naught t goes to 0, so we have delta theta equals 1/2 alpha t squared, and that means alpha is 2 delta theta over t squared. And so plugging in here, we have 2 times delta theta, 140 radians, over t squared, so that'd be 60 seconds, and then square that. And when you do that math, 2 times 140 over 60 squared, you end up getting 0.077777 repeating radians per second squared. And so to 2 sig figs, we will call that 0.078 radians per second squared. Now that you have your alpha, you have a choice of what to use to solve for the final angular velocity. But to my mind, this equation seems the easiest. Omega final equals omega initial plus alpha t. And of course, because this thing starts from rest, you end up with just omega final equals alpha t. And when you do that math here and plug it in here, you get the alpha that you just found, 0.078 radians per second squared, times the time, 60 seconds. And that gives us a final angular velocity of 4.68 radians per second, or to 2 sig figs, 4.7 radians per second. And of course, that's not it, because the problem says, what is the final angular speed in revolutions per minute? And so now we have to go and convert it back. And what you'll notice here when we go and convert it back is the answer is pretty straightforward, I think. We end up getting 4.7 radians per second. We multiply this thing here by 60 seconds over 1 minute to make the seconds cancel. Then we multiply here by 1 rev over 2 pi radians to make the radians cancel. And we're left over with revolutions per minute. And when you do that, you get 44.88 revolutions per minute. And so we'll call our omega final 45 revolutions per minute. And that's it. Now, if you were thinking here, the final velocity should just be 23 revolutions per minute because it makes 23 revolutions in 1 minute. It's important to realize that would be the average velocity or average angular velocity. And so if it's experiencing a constant angular acceleration, all you need to do is take that angular velocity average and multiply it by 2. Now, ultimately, the answer here came out to be 45 and not 46 because all of the intermediate rounding we did, but close enough is good enough as per usual. All right, and with that, that is it for this video. Before we go, I want you to solve one last problem on your own and submit this as your assignment for today. This problem says a cooling fan is turned off when it is running at 850 revolutions per minute. It turns 1250 revolutions before it comes to a stop. What was the fan's angular acceleration? Assumed constant. And how long did the fan take to stop before it came to a complete stop? Or how long did it take the fan to come to a complete stop? This question, of course, is in the rotational motion packet on page 3, number 20, but you could just go ahead and pause the video right here and write down your list of knowns. You do the work for parts A and B, answering A, the angular acceleration in units of radians per second squared, and B in units of seconds, of course. And when you're done with that, you could submit that for your assignment, and that is it for today. The answer will be shown at the top of tomorrow's video. Have a good one, everybody.